All right, so today we're going to talk about confidence intervals, uh, where we're going to figure out how to give more precise language for when we are estimating an unknown population mean mu, or proportion p, using a sample. So for an unknown population proportion p, we would use a sample proportion p hat to make that estimate. And for population mean mu, we would use a sample mean x bar to make that estimate. So we've sort of said before that when we take a sample mean, that mean should be approximately equal to mu. But saying something is approximately equal isn't really informative enough, right? So we need to be a little bit more precise in our language about what we mean when we say x bar is approximately mu. And the language that statistics uses for such an estimate is to describe both how far away we think our sample mean is from mu and how sure we are that it's about that far away from mu. We put those two pieces together in what's called a confidence interval for mu. So every time we take a sample and find a sample mean that we expect approximates the unknown population mean, what we do is we give a range based on that sample mean where we're pretty sure the true mean has to be. So we're going to set up all of the language and notation we need to construct and interpret confidence intervals. In a separate video, we'll see how to do confidence intervals and things like critical values using StatCrunch. And then we'll also do a few examples. But the purpose of this video is to kind of run through the construction of a confidence interval that's done in the notes. So I hope you've had a chance to read over that. We're going to do it slightly more generality than is done in the notes. But the good news, I think, is that all of this really is based on things that we know and know how to do. But they're kind of packaged in a slightly different way. So we have some new language, a little bit of new notation, but it's based on the material we've just done, which is the central limit theorem. Okay, so here, let me remind you what the central limit theorem says. Right? So roughly, if we take a sample mean x bar, so we've taken a simple random sample of size n from the population, and found the mean of that sample. The central limit theorem says that that sample mean has a normal distribution with the same mean as the population. So x bars are all centered around mu, the thing we're trying to estimate. And then we have the standard deviation for x bar, sigma over root n, which tells us how far away we expect x bar to be from mu. And because it's a normal distribution, we know a fair amount about the percent chances that x bar is a certain distance away from mu. So the general setup is that we're going to let z star, right, so we have minus z star and z star. This is what we're going to refer to as the critical value in our confidence interval, but it's not new. Right? All z star does is it tells you how many standard deviations away from the mean you have to be so that you have c% of the area of your distribution over that range. So the empirical rule, for example, says that if we want 95% of the area to be caught between these 2 points, then z star has to be about 2, right? 2 standard deviations away from the mean in a normal distribution captures 95% of the area. If I wanted to expand that out to 99.7% of the area, then I hope you recall that z star would have to be about 3. Now, we've seen limitations of the empirical rule in our homework where, for example, if you want the cut off for the middle 97% of the area. The empirical rule doesn't tell you that, right? So for that, you go to StatCrunch. Or if you want a more precise value for Z star, even for like 95% or 99.7%, you go to StatCrunch also, where you'll find that for 95%, Z star is really about 1.96, so really close to 2, but not quite 2. And for 99.7%, I think it's a little shy of 3, like 2.97 or something like that. Okay, so we have this setup for the normal distribution for our sample mean x bar. And one way to interpret this setup is that there's a C% chance that x bar would land within Z star times sigma over root n of the true mean mu. So if you plucked a sample mean at random out of all possible sample means, there's a C% chance it's going to be inside this interval, where we're going from mu minus Z star times sigma over root n to mu plus Z star times sigma over root n. All right, so here's kind of the rationale for how we construct the formula for a confidence interval. As we just mentioned, there's a C% chance that a randomly selected x bar is going to fall within the critical value Z star times sigma over root n of mu. For the 95 level, which is done in the notes, there's a 95% chance a random x bar is within 2 sigma over root n of the true mean mu. Well, this is sort of like the one step that may take at least a moment for it to make sense. And the idea is, if I am, let's say, 6 feet from that wall, then the wall is 6 feet from me. Right? So that's basically just kind of reversing the point of view for that distance, right? If I'm 10 feet from a chair, the chair is 10 feet from me. And that's really a crucial step in developing the confidence interval. Because at first we start with, there's a C% chance x bar is within Z star sigma over root n of mu, but that also means there's a C% chance that mu is within Z star sigma over root n of our x bar. And it's kind of an important step because x bar is what we know. Okay, that's the thing we actually calculate from the data. Well, if there's a C% chance that mu is within Z star sigma over root n of x bar, that means we're C% certain that mu is within Z star sigma over root n of x bar, which means we're C% certain that mu is in the interval x bar plus or minus that distance. So on an exam, I would accept either form of the interval. You can write x bar plus or minus Z star sigma over root n, or you can do x bar minus Z star sigma over root n to x bar plus Z star sigma over root n. Well, this last bit here is the C% confidence interval for mu, right? We're C% sure that whatever our x bar is, this interval that stretches from x bar minus Z star sigma over root n to x bar plus Z star sigma over root n, we're C% sure that the true, though unknown to us, mu is in that interval. Right? So that's our construction of a C% confidence interval. That's based on the normal distribution. There's a little bit of extra language. I think we already mentioned that the C% critical value is the Z star. That's the point where you have the middle C% of your area under the normal curve. Right? And we'll take a look how to get StatCrunch to produce the Z star for general values of C, not just 95 and 99.7. And then finally, the thing that we're plussing and minusing around x bar, the z star sigma over root n, that's called the margin of error of the interval. Right? So if we had x bar plus or minus 3, the margin of error would be 3, and then the confidence level tells us how sure we are that we're within the margin of error for mu. All right, so that's the kind of concept of a confidence interval. Next, we'll do a couple of examples, and there'll also be at least a brief video to show how to get StatCrunch to do the things that we need.